folks. Welcome to the third unit of our CIP classes in this year's Masters. My name is Sean Ching, and here's my colleague Justin Osh. I'm representing the 8-bit solutions for Microchip, and Justin is from our 16-bit department. Today we're gonna do our third part of the CIP class. We're gonna introduce what other ways of applying our CIPs for some data communication protocols. The objectives of our class today is we're going to cover some of the CIPs that we designed specifically for some of the data communication applications out there. After we cover those, you should be able to get familiar with what those CIPs are, how they work, and what they are used for. And you should be able to select and combine some of the CIPs and come up with a solution for your own data communication requirements. And you can also design efficient communication application systems based on the selection of CIPs and based on your system requirement. So that's the goal of this lecture today, and we hope that we can cover all of them after this class. So today's agenda is pretty straightforward. We're basically going to go over all the available CIPs, what are they, and why and what and why are we using them. Then we will dive into some detailed examples of those CIPs, how we use them, and what we can use them for the data communication applications. And finally, we're going to summarize today's lecture. All right, so first let's take a quick overview of those CIPs. Well, for those of you who already taken the previous CIP courses, CIP 1 and 2, you might already seen those overview slides. So just think of them as a refreshment of your memory, right? It might be identical of those slides because most of us come up with the same slides. So CIP stands for Core Independent Peripherals. It's a module that is self-sustaining. It's a peripheral, hardware peripheral that removes a complete task from the CPU, so you can free up your CPU, free its power, free its cycles. If you want to do some other computation, you can use the CPU to do those computations. If you don't want to do any computations, you can just put your CPU into sleep so you can save power. And CIPs are a collection of peripherals that implement a complex system, right? So it can handle all those requirements out there depending on what your application requirements are. So why do we use them? Well, as we mentioned before, it's going to help you reduce your CPU overhead. It will reduce your power consumption if you decide to put your CPU into sleep or idle. And it reduces hardware and software complexity. And why is that? Because most of your design requirements, most of your designs can be offshelved to the hardware-specific design, the components on the die, which intrinsically reduce your cost of buying discrete hardware components or external hardware components. And you don't have to worry about the software routines emulating something in software because those are handled by the hardware. So those are the basic idea of why we come up with those CIPs to help you facilitating your design. How about those CIPs for data communication? That is the topic of our class today, right? We do have some dedicated CIPs that design specifically for some data communication protocol applications. Besides that, you can also come up with your own combination of different CIPs to serve your own data communication requirements. And there are examples in the future slides that we can see what we mean by combination of different CIPs. So for data communications, what CIPs are available out there? Well, we have a bunch that either designed specifically for a data communication protocol like send and ask/RS, and we have other CIPs which are more general CIPs, but they can be used in a creative way of applying your satisfying your data communication requirements. So don't be scared by those acronyms. We will dive into each of them in the future, in the following slides. We have also, well, of course, classic data communication CIPs, right? Those serial communication, UART, SPI, and I2C. For the sake of completeness, we'll just briefly touch them because It's just universal, it's everywhere. We have also other CIPs for a more complicated or more complex system, like USB and LIN bus and CAN bus, and some other maybe unrelated, not directly related to data communication, but they can be applied in a creative way of serving your data communication requirements. However, those two we are not going to cover today. So for the CAN, USB, and LIN bus, we have specifically designed classes in this year's master, and you can take those USB 1 to 7 classes and CAN 1 to 3 classes if you want to know in more details about those. And we cover other CIPs in our other module of our CIP series this year. So if you're interested, we are recommending you taking other CIP classes. All right, so that's basically the overview of what we have. So how are those CIPs working and what we can do with them? So let's dive into them with some examples along the way. So the first one we're going to look at is DSM. It stands for Digital Signal Modulator. So it is, well, as the name suggested, it is a CIP that we designed specifically for a digital data signal modulation. So when we're talking about digital signal modulation, what are those most popular digital signal modulation methods out there? Manchester, that's one of them. It's more like coding-ish, not very on the modulation side, but that's a good one. Yeah, modulation, like I have ones and zeros, I want to send it out, modulated on different frequency, right? Exactly, like FSK, OOK, right? So the first one coming to our mind probably is FSK, just refresh your memory. What we do with FSK is we have a modulating signal, that's your original signal. You can pick 2 different frequencies for your carriers. You have carrier high and carrier low. You modulate your modulating signals onto those different carriers depending on its logic 1 or logic 0, and you got your output. When it's logic on, it might be a higher frequency. When it's logic 0, it might be a lower frequency, right? The same principle applies for OOK. The only difference is now your low frequency carrier is just DC. So when you have a logic 0, you simply just output nothing. You just output a DC. And then when you have a logic 1, you have your output as your carrier high frequency, right? The other one is PSK. Well, instead of using different frequency for your different carriers, you just simply use the same frequency but with a phase shift. So for example, if you have a 180 degrees phase shift, then you get this complementary waveforms with your modulating signal modulated on that. Your output will be something like this, right? Make sense? Right, so, okay. So after we've seen this, we figured out, wait, so those modulation methods, they pretty much have the basic same structure, right? I have a modulating signal, and I have 2 carrier frequency signals, and I get the output. So that's pretty much what our DSM module is doing. What we're doing is we take 2 carrier frequencies you can choose from various sources. They are carrier high and carrier low. You're taking your modulating signal, and you do some magic here, you get your modulated signal.
This can be done with this CLC?
Correct. So CLC, you can configure in multiple ways inside CLC to serve the same purpose. But DSM is a specifically designed hardware just do this. Make sense? Yep. All right, so in a nutshell, what's happening inside this is you actually have a switch. It's going to be either on the high side or low side, depending on your modulating signal. If it's 1, then it's going to be on the high side. If it's 0, it's going to be on the low side. Make sense? That's naturally serving as our FSK, OOK, and PSK modulating. And how we do that? Again, you just fit into different frequencies for your carrier, high and low, and get your modulating signal, and you get your output. If I get a frequency and a DC, I got OOK. I can do FSK with 2 different frequency carriers, and I can do PSK with the same frequency carrier, but with 180 degrees phase shift. right? Now, what can we use as the input for our DSM? For your modulating signal, you can choose a bunch of signals internally or externally as your input signal. You can choose your CCP, you can choose your PWM output, you can choose your SPI, comparator, UART, Unseal, COC. It can also, of course, coming out from an external pin as your modulating signal. And it could be also set in software. So you write your data to a register, it's gonna output according on the content of your register, right? For your carriers, again, you have a lot of selections available here. You can do CCP, PWM, FOSC, high frequency internal OSC. You can provide a reference clock, of course, and Unseal, COC, external pin, and a DC, which can be used for OOK, of course. Now, some other neat features we have with DSM. We can choose synchronization schemes. We will dive into details about how the synchronization works in the following slides. We can choose polarities on both your carrier source and modulator output, so we can flip them around. You can program the modulator data. This is the software-controlled modulating scheme, right? You have multiple input sources available, and you can control the slew rate. So those are pretty much trivial, but I do want to get into a little bit more on the details about the synchronization. So when we're talking about synchronization, we have a glimpse inside this DSM, see how it works. So DSM, in fact, is nothing but a simple structure like this one. This is actually an upside-down mirrored structure, except there's a little negation gate here. So if you ignore this one, those two are symmetric, right? So let's just focus on part of it, so it's going to be easier to understand. When we're talking about the DSM, inside is just a switch going back and forth, back and forth. And if right now I choose to ignore the synchronization, what actually it does, some of you might already guessed, it's just an AND gate, right? So if I AND my modulating signal with my carrier, whenever my modulating signal is high, then I get exactly what I have on the carrier signal, right? And then of course, on the low side, you do the same thing, and the output of your low side and high side just ORT together. So you can choose between high and low based on your modulating signal. Now, that's without synchronization. If I have synchronization going on, I set this max to 1, then my signal flow is going to go this way. This tells me the output of my D flip-flop is synchronized with the falling edge of my carrier signal, right? So it will not change its output until I see a falling edge on my carrier signal. Make sense? So in a nutshell, whenever we're talking about synchronization for this DSM module, we're always talking about synchronized with the falling edge of your carrier signal, either high or low. It's the same thing, right? Now, since we have two of them, one for high, one for low, things will get a little bit trickier when we just setting one of them or both of them. So if we don't have synchronization at all, this is a trivial case. It's just going to copy whatever is available on this carrier frequency and just do exact copy, and happens exactly at the transition of my modulating signal, right? If I have a single synchronization setup, either for the high side or the low side, what's going to happen? Well, as we mentioned before, it's going to try to synchronize with the following edge of my carrier frequency, right? So in that case, if my transition on the modulating signal is from the synced side, for example, if I'm setting my high side as synchronized, and high side basically means it's going to be active when my modulating signal is high, right? If I'm transitioning from this one, means I'm transitioning away from 1 to 0 on my modulating signal. What's going to happen? Because I'm transitioning away from this synced side, the unsynced side, the other side, will be active immediately, because this one is not synchronized. So it's gonna immediately copy whatever it is on the other side, for example, the low side, right? And then on the synced side, as we mentioned before, it's always gonna do the transition on the following edge of my carrier signal. Make sense? And the same thing happens when it is transitioned to the sync side. The unsynced side will become inactive immediately because I'm transitioning to the sync side. So the other side will become inactive. And the sync side will become active on the following edge. Make sense? So for example, I have a little sequence here. This is my high side. This is my low side. For some reason, my low side frequency is higher than the high side, which is ironic. This is my input, or this is my modulating signal, right? So if I am synced with the high side, what's going to happen? My transition happens here, but my high side will not become inactive until the following edge, which means around this area, both of my high side and low side are active, right? Because my low side will become active immediately, and my high side will stay active until I see the following edge. Make sense? If I do the other transition, I'm transitioning from 0 to 1, well, my unsynced side will become inactive immediately, and my high side will stay inactive until the following edge here, right? Which means at this point, nothing is active on the line, so I will get 0 output. Make sense? Awesome. Now, a little bit more. How about dual synchronization? Dual synchronization, well, ideally, you will say, okay, I just apply the same principle. Both of them going to wait for the following edge. Yes, in principle, that is correct. The only caveat here is whenever you do the transition, if you transition from the high side will be waiting for its following edge for sure, but the low side will be waiting for his following edge after the previous following edge on the high side happened. So in other words, if I'm transitioning from one side, let's say high to low, then the transition from side has to be synced first. Then the transition to side will be synced on the following edge, given the other side is already synced. Make sense? Example again. The same setup, high, low, modulating, and output. My transition happens here. I'm transitioning from the high to low. So the first thing should happen is the following edge of my high side. After this happens, I'm waiting for the following edge on my low side. After I saw those, okay, I'm good. I've finished all the transition. Now it's going to follow whatever it is on the low side. Make sense? And the same thing, if I have a low to high transition, the first following edge I'm waiting for is on the low side, right? So I'm going to see the following edge on the low side first, and then I'm going to keep waiting until this guy happens. So at this point, again, nobody is active. So I see a DC output on the output 9. Any questions? Awesome. All right, so since we already figured out all those synchronization stuff, then some examples are going to become straightforward. If we apply FSK, well, we apply two different frequencies for our carriers. Then we get the output. If we don't have synchronization, it will just do exact copy, and the copy will happen at the transition points. If I do PSK, well, I apply high and low with a phase shift. I can apply no synchronization, high side, low side, and both sides. What you will see, the waveform get a little bit distorted depending on what synchronization you choose. for better or for worse. So that's the DSM. Any questions on this module? Awesome. All right, so the next one, or actually next two CIPs we're gonna look at is Unseal and CLC. How many of you guys already seen CLC slides this morning? Awesome. Okay, refreshment of memory. Well, actually not. It's only 2 hours. So CLC stands for configurable logic cells. That is something we designed and we decided to put in the die to help you facilitate your designs. So what does this actually is? It is actually a peripheral with configurable basic logic components. So when we're talking about logic components, what we're talking about here, we're talking about different gates, flip-flops, and latches. That's some discrete. Well, usually if you need those, you would just go by some discrete components like 7/4, right? But those, first of all, it's gonna be some extra cost to your board, even though those are cheap, and it consumes up your PCB areas, right? So to save your money and time and your PCB areas, we come up with the CLC module, which is on the die. You can configure them as different logic components like gates and flip-flops and latches, and you can use. The best part of it is very flexible. It has very flexible interconnectivity. It can literally choose whatever internal signal it is available from almost every other internal components that you can use. So the input to the CLC can be from mostly every other CIPs you have in the die. So for example, you can choose your PWM as an input, you can choose your timer as an input, you can choose your CCP as an input, Unseal as an input, and et cetera, et cetera. So when talking about those components, what we have is we have 8 of them that you can choose from. We have 3 different gates, and OR gates, or XOR gates, and AND gates. We have SR latches and D latches that you can choose. We also have D flip-flops and JK flip-flops you can choose. The inputs, as we mentioned before, is selectable from nearly every peripherals and, of course, I/O pins on the device. And the output can be steered to many of the peripherals as their inputs too. So it's like you can choose it as a man in the middle and just do signal conditioning or signal conditioning for the output, right? So a basic structure of this, how the CLC looks like. We have, as we mentioned before, you can choose from one of the 8 logic components, and the input of them, you actually have in total 38 different input selections that you can choose from. And the inside of this, don't be scared by this part. This part is just the output, latches, and interrupt generation, so we don't care about those. The really 2 main components that we have in the CLC is the first one, the input data selection stage. That's where you choose, okay, which input I'm gonna use for the CLC. The second one is, of course, which logic components you're gonna configure the CLC as. Either it's be a gate or be a latches, right? So when we're talking about the data selection, what do we mean? Well, again, you have 38 different input you can choose. Those basically can cover all the internal peripherals, and you can, of course, configure them and output input pins, physical pins on the device, right? And then you mux them in. You get the signal itself and the negation of it. By writing those bits, and those bits are mapped to a register, you can actually choose the signal itself or the negation of the signal itself, right? And those are all AND together and ORed, XORed, get out. And this becomes G1, we call it a candidate input to the second stage. So for each CLC, we have 4 of those blocks, which gives us G1 to G4 as the input candidate, right? Now you might be wondering, okay, what values should I put here? This slide tells you what values you should put here, but I'm just only putting this slide here for your reference because in practice you don't really need it because we have a neat tool called MCC. You open it, it's a graphic user interface. You open it, you just click, I want this one, and it will generate the code for you and fill up the register for you. So this is just, if you really want to go hardcore, well, this is the register you're looking for, right? Now, as we mentioned before, we have 4 candidate inputs, right? G1 through G4 from the first stage. The second stage, we take those 4 candidate inputs, and we can configure our CSC module as one of the 8 different logic components, and you can fit those signals to the logic components to serve your purpose, right? Any questions on CLC? Awesome. I know you might get bored because you haven't seen this, right? But now there's a new one. Unseal, numerical controlled oscillator. This is nothing new, right? I believe most of you guys already either heard about this or used this before. Unseal is nothing but a 16-bit increment with a 20-bit accumulator. So it's kind of like a counter, keep counting, right? And then we have a 20-bit accumulator sitting there as your bounds. When you write your increment steps, it will just keep incrementing based on what clock source you provide to this Unseal. And whenever your accumulator overflows, it will generate a signal output. Then you know, oh, it overflowed. I might have just passed this many of counts, right? We have 2 working modes for the RNCO. The first one is fixed duty cycle. For the fixed duty cycle, RNCO module provide a 50% duty cycle. And we have another mode called PF, which is pulse frequency mode. And this one let you count a specific number of pulses, and then it will shut itself down. So how do we use that? We will see examples soon. Well, again, the internal of this guy, we don't care about this part. The first part is you pick up a clock source for the NCO to start the counter. You have your counter and the 20-bit accumulator. Whenever your accumulator overflows, it will generate an output, right? Now, if we do the fixed duty cycle mode, which gives you a 50% duty cycle, we actually have 2 D flip-flops. So this guy is just serving the purpose of dividing the frequency in half, so you get 50-50. If you do the PF mode, what you actually have is the overflow goes here, the same clock source goes here, your overflow is going to set the output of this guy. When it is got set it will also enable a ripple counter. The ripple counter is going to start counting at the same frequency of your clock source to the NCO, and it will reset the output back to 0 after you have already counted this many of the pulses. Make sense? All right, so with those 2, you might wonder, okay, why do we even care about NCO? Well, sometimes it turns out if you apply them in a smart way, you might achieve some application requirements without really going hardcore in the software. So the example application we're going to look at is we're going to do a Manchester decoder with some of our CIPs with minimum intervention in the software. So just a quick note, because yesterday when I was doing this, somebody asked, okay, why we're not doing Manchester encoder? Actually, we already covered that one. We can do that with the first one we introduced, DSM, exactly. So we can do Manchester encoder with DSM easy, no problem. That's straightforward, right? But decoder is kind of trivial. It's kind of like not trivial. So we're going to look at how are we going to apply our CIPs. Well, just refresh your memory. Manchester coding is actually coming with two conventions. One is the G.Thomas convention, where your logic 1 is encoded as a falling edge transition, and 0 is the rising edge. And we have the IEEE 802.3 convention, which is the opposite way. For this example, we're going to use the G.Thomas convention, and we will use COC and Unseal to achieve this purpose without writing any software.
But you could set it up so it does,
Yes, yes. Okay, so how are we doing this? Well, the basic idea is, because it's Manchester code, right? So I will have a transition happen. I will always have a transition happen for each bit, either it's falling edge or rising edge. If I can figure out a way of sample the data at the right time, then I might be able to recover the data. So what do we mean at the right time? Suppose I have the Manchester code coming in, and the transition happens in the middle. If I know where the start is, and I sampled my data at the 3/4 of my bit time, then I am guaranteed I will get the sample after the transition. That's where my data is already stable and the transition happened. If it's 1, then I get this guy. If it's 0, then I get this guy here. Make sense? So think about your bit time. Let's say it's 40 microseconds, right?
You're referencing by the rising edge, is it correct?
Yes. So we're using the first convention, right? So your logic 1 is the falling edge. Your logic 0 is a rising edge. So we call this a bit time, right? So this is 1 bit, and this is how much time it takes to see on the line, right? If I sample my data here, the 3/4 of the time after I see the first rising edge or falling edge, then I know this guy already happened and this guy is not happened yet. Then if I sampled as a low, then I know this is a 0. However, if I sampled as a high, this is a 1. Make sense?
So you're referencing any edge?
Yes, because the nice property of Manchester code is the clock information is embedded in the code because it's always changing, right? Either it's 1 or 0, I will have an edge, either rising edge or falling edge. So that naturally gives you the clock information. Make sense? All right. So if I'm sampling at the right time, I should be able to recover the data, right?
Please, could you come back a little bit?
Sure.
Just again.
Yes.
If you have the first going down edge key.
Yes.
Here, okay, and you are sampling the third part in the third quarter.
Here, yeah.
So you're sampling low. You're sampling 0.
Correct.
Okay. But what if in this situation? What if you you wanted to transmit 1 instead of 0? How would be this?
Okay.
wave?
So if you do this, right?
But you must be in the first. You must be okay. Let's say if I want to send 1 and 1.
Correct. Okay, that's a caveat I'm gonna cover. The only caveat with this solution is you're always gonna miss the first bit, because I'm not sampling the first bit. Because the first bit, what I'm using is I use the first transition as my synchronization. Exactly. That's a very good point. So the first bit, I'm gonna miss it. And then that can be easily covered by your application. For example, you can just put a dummy bit as the first bit when you're transmitting any data. Yes?
It's not like the sampling is very similar to asynchronous communication protocol with UART.
Right.
So once you get the first transition, you have a set speed of data you're expecting.
Exactly. And you know the clock because it's embedded. It happens every transition. Make sense? All right. So suppose I can do that. Then let's assume we have a decoded clock. Then what I do is just I will make this clock a 75% duty cycle, and then I will just synchronize with the rising edge and sample at the falling edge. Make sense? Yes?
You don't synchronize on the very first rising edge?
Or falling edge. So the first,
If there's a drift, you've got a couple hundred bits, and you're off by a little bit, you're going to get kind of screwed.
I'm sorry, say that again?
So, I mean, how do you account for any drift between the clock that's coming in and your reference clock? Does it resynchronize every edge?
Okay, so there's no clock, right? So the clock is in the data. Because I am doing my transition for each bit. For 1, I have a rising edge. For 0, I have a falling edge. So I don't need a clock. The clock is already in the data. So depending on how fast your transition is, you can naturally recover the clock. Make sense? Are we good? Everyone good on this side so far? Okay. So that is how you recover the data, right? Now, we've been talking about this based on the assumption that we have the clock, but actually we don't have them yet. Now, how we recover the clock? Well, if you look into the textbook examples of Manchester code, when they're talking about, oh, okay, Manchester code is very smart, the clock is in the data, and we can always recover the clock from the data. And the example they're going to use, as always, is, okay, you just XOR your input data with your recovered data, then you get your clock out. So what we mean by that? Suppose we have a decoded data, and we have input data. Well, since I'm having my transition for each bit, if I XOR them together, I will always recover a rising edge that is perfectly synced with my input data, right?
Yeah, it's strange because you have to sample in the third quarter of the wave, but you don't know where the wave will finish.
Right. So
How can you know where is the third quarter of the wave?
okay, that's actually what we're going to cover. I know where the third quarter, 3/4 of the time is because I can get information about the period.
Just after it has gone down.
Yes.
Okay, but you're stating that you have to sample it in the third quarter and you still don't have the information about when it goes down.
I know the information about when the clock starts. I know the information where the first transition happens because that's embedded with the data, right? If it's 1, then it's a rising edge or falling edge. If it's 0, it's the other way around. So when the data comes out, the first transition I can always capture because it's by the definition of the Manchester code, right? It's a non-return to 0 code. Make sense? So the first bit, whether it's 1 or 0, I will always have that transition going on. Either it's rising or following.
Okay, go ahead.
Yeah. Right. So with that, if I XOR them together, I get a semi-working clock source. However, this is not a perfect clock, right? The only thing I can guarantee, if you read some textbook, the only thing I can guarantee is I can synchronize with the transition on the rising edge. But my following edge, well, it depends. If it's a 1 here, following by a 1, I got cut off here because there's a transition happening and I do XOR, then it's going to be a transaction happening here. If it's 1 followed by a 0, well, there's no transition happening in the middle, and then I do XOR, I get this a little bit wider on time. Make sense? Awesome. So now we are pretty close to what we want, right? So we want synchronized with this clock, and we want to do our sampling at the 3/4 of the time. Sometimes we get the right time, but sometimes we are 20%, 25% off because of the data pattern in your data. So what we want to do is we want to make this imperfect clock perfect. So we want to actually extend those situations and make them a 75% clock source. That way, we have a perfect clock, we synchronized with our data rate, and we can do our sampling on the following edge of our recovered perfect 75% clock. So far, so good. All right, so that's where our NCO might came into play. So remember that when we're talking about NCO, we mentioned there's a PF mode, pulse frequency mode, that gives you a certain number of pulses and then it will shut down itself. We can apply that to extend our imperfect clock to a perfect clock. So what we do here is those parts are the same, but if we look at the clock, whenever I see the rising edge, which is synced with my data rate, I start counting my NCO. And I configure my NCO in such a way that we will count 3/4 of the time of my bit time. Then it will shut down itself. Then I ORed my imperfect clock and my output of my NCO. So naturally, whenever this guy is available and this guy is still counting, I will output a 1. When this guy got chopped off because of the data pattern, 1 followed by a 1 here, but my NCO is still counting, I will just keep my output as 1 until my counting is counting down to 0, or the value is set to. That way, I can extend those unfortunate cases into a 75% duty cycle. Make sense? All right, so those waveforms might be a little bit convoluted, but once you say this, it might become clear, I hope. So again, as we mentioned before, when we do data out, which is pretty simple, I have my data in, my output data, it will just based on sampling at my 3/4 of my bit time. So if I configure this clock correctly, then the data out is just trivial, right? I'm sampling at this age, following age, right? Now, how do I get my clock? Well, as we mentioned before, we do data out and your data in, we XOR them together, give you the imperfect clock, right? I got my imperfect clock, which is a green line here, a green wave here. I OR them with itself, I OR it with the output of my NCO. Well, the NCO, because remember, we need to provide a clock source for the NCO, right? So here we just arbitrarily select fosc as a clock. So I put this fosc to 2 AND gates, one added with my imperfect clock, the other one is my clock output. Then I OR them together. This becomes a rear clock source to my NCO and output feedback to this AND gate. So what happened here is when my imperfect clock is valid, this guy becomes a valid. It got ORed to here as the clock source. So it will keep my NCO running, right? When I got chopped off by this 1 followed by 1 pattern, the other way around, my NCO still keep running. It will make this AND gate available and got ORed here, provide a valid clock to my NCO, and my NCO will still keep running until it hits the PF mode register, which is how many counts you specify, and then it will shut itself down. It outputs the following edge. The following edge will, first of all, feed back to the following edge data sampling here, and it will shut this guy down. Suppose this guy is down already, and if after this guy is down, then it will shut my NCO off. That gives you a perfect clock source as a black wave. Make sense? Awesome. All right, so the only missing part is how do you configure your NCO, right? Well, this is trivial. If you know your data rate, you just calculate the 3/4 of your data rate of the period of time and fit that value to your NCO increment value. given what f-ask it is on the device. Make sense? All right. So again, I think I'm missing an animation here. The only caveat for this one is your first bit will be missed. So that can be easily compensated by either transmitting a known first bit or just transmitting some dummy first bit in the software. So that's the only caveat here, but it's much better than doing bit banning, I hope. Now, another CIP we're going to take a look at is CCP, which is Capture, Compare, and PWM. This, again, is very popular and universal everywhere. So I just briefly go through what they are. Capture is nothing but a timer running in the background and trying to capture some events. When the event happens, either rising edge or falling edge or both of them, it will capture the counter which is running in the background and save it to a register so you know, okay, how many counts have passed when I see this event, right? A compare mode works the other way. What you have is you set up a register for the counter as the compare value, and you have a timer running. Whenever those two values matches, it will output generate an event, which is levels or edges, depending on your configuration. And PWM is just an enhanced version of the output compare. You can actually specify your duty cycle and your period through this timer module, and it will generate your PWM waves, right? So you might be interested, okay, so why we're talking about this, like everybody is using it. Well, it turns out with the help of other CIPs, we might be able to do some interesting application examples without writing any software. So one of the examples we have, actually, it's a lab that you can try it out this afternoon, is we can do a SOS generator in Morse code, drive a buzzer. Actually, we're running out of buzzer, so the lab got modified a little bit. Now it's just lighting up a LED to generate a periodic Morse SOS signal. So this is purely CIP-based, zero coding, and you can configure everything through MCC. So no coding, no register, datasheet finding, just pull up MCC, configure those peripherals, connect them together, and then you'll see SOS lighting up on your LED continuously. So if you're interested, try out in the lab. All right, so next, my coworker Justin is going to cover some of the 16-bit specific CIPs that might be interesting for data communication protocol applications.
All right, thank you, Sean. Again, my name is Justin O'Shea. I'm in the MCU16 applications group, and today I'm going to go over PTG, I2S, and the CENT module that are found in the 16-bit products. We'll start with the PTG. So, I know it's 2 o'clock and it might be a little sleepy, so we're going to go through the super exciting programmable trigger generator. So I'm sure everyone will just be excited. So what is that? It's a sequencer that's used to generate triggers. It allows you to make some more complex triggering algorithms without using the CPU itself. It's integrated with some of the other peripherals. And I think the history behind the PTG is that it was originally, I believe, designed to trigger an ADC for PWM applications. So a lot of times you need to come up with a complicated scheme to know when to measure a current or voltage. And it's also useful for a bunch of other things. And that's kind of one of the reasons why we're talking about it today, is like the CLC, you can do a lot of stuff with it, and you're only limited by your imagination. So, talk a little bit about the features of it. The sequencer is built from what we call step commands that are stored in a queue, so you would figure out what you want to do and put them in that queue and it'll execute them. Those commands include delays, which either step delays or from timers, waits and waiting for inputs, so conditional things. It'll do looping, including nested loops and conditional loops. It also has 2 dedicated timers, which is an important feature for doing delays in that you don't need to use one of the other system timers. So, does anybody know why you wouldn't want to use maybe timer 1? Well, usually you'd have to use an interrupt to get the overflow or a compare from that. So, since the point of these classes are to be core independent, this one has its own timer and it's built in, and you don't need to use any code in interrupts to stitch these solutions together. It also has a dedicated watchdog timer in case you maybe never get an input or something has gone wrong in your system. So what can it be used for? Well, all kinds of things. In the context of communications that this class is about today, you could use it for generating or controlling waveforms. And you could use either that PWM or the output compare function of the CCP to do that. You could create gated pulses or variable frequency waveforms. Another thing you could do with it is to do pulse width detection using the input capture peripheral. And another good feature of the PTG is that it actually will drive an external pin. So you can come up with a solution that is almost external, like hardware, to the part. It can also be used to control another peripheral. Again, that was kind of the original intent with the ADC. And many other things can be done with it. So I encourage you to take a look at these. This particular peripheral, I think, is becoming more important and asked for by our customers. So most all of our new parts that are coming are going to have a PTG in it. So some additional info that you can find on our website about the programmable trigger generator is there's an app note, 2152. There's also a family reference manual, or FRM. So in 16-bit division, we have a FRM for every peripheral in our part. Otherwise, the data sheet would be 1,500 pages. So take a look at that if you have more questions and want some detailed information on what exactly all the commands are and what inputs and peripherals are connected. And there's also some more information here today and for the rest of the week in Masters, including some material in CIP3. Has anyone taken that class? No? You have? Okay. And there is also some material on that in the Open Lab session, which is today, tomorrow, and Friday as well. Does anybody have any questions on PTG? All right. The next peripheral we're going to look at is the CENT module, which is a fairly new one. So what is it? CENT stands for Single-Ended Nibble Transmission. And it is a communication protocol that was developed by SAE, which is Society of Automotive Engineers. And it is a unidirectional single-wire protocol that was developed for point-to-point transmission of sensor data. The intent of developing this was to come up with a low-cost solution, and also it's single wire, so reduction of wiring in a car, reduction of weight. What makes it lower cost? Well, one of the main things is that it doesn't require an accurate clock, so you probably don't need a crystal. You could use the internal oscillator, and it's hot under a car hood, so if that oscillator drifts 1 or 2% or 10, you're okay. It'll handle up to 20% drift. And that's done by how the receiver synchronizes it, which we'll get into a little bit later. The other benefit that it may have over another solution is that it doesn't need a differential or high voltage driver like some of the other ones do. So how does it work? Well, the messages are encoded in the time between falling edges. And the system is based on what they call a tick time. And that is predetermined time period that both the transmitter and a receiver are already aware of, so they know what synchronization pulse it should be looking for. It also has built-in data error detection in the form of a CRC, so the hardware calculates that. You don't need your processor to either generate or validate a CRC. And the module in our devices will support both transmit and receive modes, so you could build a sensor or some other type of engine computer or what have you with our devices. So we're going to look at the message format real quick. It starts off with a sync period, which again is for the clock synchronization. And the hardware is always looking for this sync pulse, so if something gets reset or something gets corrupted on the bus, it can find a new sync pulse and it won't hang somewhere stuck in there looking for the next data nibble. The next piece is the data itself, which starts with a status nibble, which is nothing more really than another piece of data. It could be used for whatever. And then we have 6 nibbles of data, which will give you 24 bits of resolution. You could use that for one sensor, or you could mix things together and have 2 12-bit values transmitted at the same time, or any combination. And I talked about how they're encoded in time. So in this case, a value of 0 would be 12 tick times, and the maximum value of F is going to be 27. Although that might cause some problems, in that the length of the message is going to be dependent on the data. So to handle that, if you want to have a fixed length message, there's also a pause pulse that you can turn on optionally, and the hardware actually calculates how long it needs to be to pad that piece of time to get them to be the same length. So again, you don't need to use any software to figure out how long it needs to be if you want to have a synchronous mode. So a typical usage of this is going to be an automotive sensor. It's kind of what it was developed for, although you could use it for anything. That might be temperature or pressure. And there was an extension made to the specification to allow bidirectional communication in case you wanted to calibrate a sensor or query it or anything like that in your system, self-test. So we're going to look at a usage example of a mass airflow sensor, which measures the airflow into the engine and perhaps temperature. So are there any car guys in this audience? Anybody into building cars or like that?
I've sworn at a MAP sensor about 4 times. So. Does that count?
That can count.
I've probably replaced 4 of them in the last year, so.
Yeah. They can be finicky if they get dirty.
I live on a dirt road. I think that's what's started to happen.
So a lot of them are based on a hot wire with the air going across the wire, and it cools it off, changes the resistance. Therefore, you can measure the voltage, and there's your airflow rating. And usually that number is sent to the computer in a raw, just counts or a value. So how does it work within the engine? Well, you figure out the flow and the temperature, you know how much air you really have, and then you meter the fuel accordingly. So when your car's warmed up and you're driving down the road, and the oxygen sensors might say that it got the wrong answer and correct it. But typically when you're at full throttle, it's just a lookup table, and you don't have that. So that's a way you can cheat, I guess, if you want to tune your engine, would be to do it through the MAF curve. And eventually, if you're increasing performance, you could get to the point where that reaches its maximum value, and then you're in trouble. So in this case, our mass air meter is our transmitter, and the receiver would be the engine control unit. And again, the ADC is in the device is going to convert that analog voltage typically into some digital value and send it off on the sent bus. Could do that synchronously with an ADC sample, or you could also have it just transmit back to back with the same value, and then when an update comes in, the data will change on the bus either way. So for some additional information on the sent, we have an FRM, just like the rest of the peripherals. So if you're interested, take a look. It's on the Microchip website and on the landing pages of the parts that have it. Last one I'm going to talk about today is I2S, which sounds kind of like I2C, but it's not. It's inter-IC sound, which was developed by Philips in the 80s. and it's a full duplex stereo audio standard, and it uses PCM encoding, which is basically taking a snapshot of the amplitude of your audio signal in time. So, is anybody in here an audiophile? The speakers? Okay. So am I. It's probably the reason why I'm an electrical engineer. I got into building speakers when I was a little kid, taking apart my parents' stuff and trying to improve upon it. So that's always something I've been interested in. So what is I2S? Well, it's actually an SPI, and it's supported by the SPI peripheral, with the main difference being the slave select line, which a lot of times we don't use, is replaced with the word select, which selects either the left or right channel data. So pretty straightforward. It's a serial 1s and 2s complement, and it supports a variable bit width, which we'll talk about a little more later. So here's a quick look at what an I2S packet would look like. A master typically supplies a bit clock, and that bit clock needs to be programmed according to the audio that's being transmitted. So in this example of like CD audio, which would be 4401K, 16-bit, 2 channels, we multiply those together, and we can see that we need a bit clock of 1.4 megahertz. The second piece is the data, which is transmitted most significant bit first, and that's done, so it'll handle data mismatches, whether or not the data is either too long or too short. If it's too long, it truncates it. If it's too short, it'll zero pad, so it'll handle that. And then the blue one, again, is the LR clock, which is just telling the receiver which channel we're on. So a quick usage example of I2S would be maybe doing audio playback from memory. Maybe you have a product that you want some kind of confirmation from a button press or some event happening, a little ding or a beep or a bleep or a voice, whatever it would be. You could put the audio data in data memory and then use the DMA to transfer it to the SPI without needing the CPU or the core to do anything, which again is kind of the point of the class. Like, how can we leverage these peripherals to work by themselves so your code can do something else or nothing? You can put it in sleep. So here we have the SPI in I2S mode and hooked up driving a codec. So quick block diagram of what that looked like. In this case, with the master is going to drive all the lines. You don't really need the direction. There's quite a few different conventions for naming the pins. Here it shows the SPI-based functions, but a lot of different companies use different names for the same thing. So some high-level implementation details. You'd want to store the data in 2's complement in the memory, so you don't have to do any processing to it, so you can have the DMA send it out directly, and it'll be in the right format for I2S. Again, you'd want to set up your baud rate, which would, the SPI speed for the audio that you're intending to send out. And the DMA, you want to have your DMA or your transfer done at the sample rate. So in this case, you could use a general purpose timer to trigger the DMA and load the SPI output buffer with the data. The SPI peripheral also has a couple other audio modes in addition to I2S, and I think they have in the past as well. So there's left, right, justified, and you can get straight PCM data, which is mono, I believe, only. So this information and more of it is in the FRM, like the others. So they're on the Microchip website. Take a look if you want to get some more information on the SPI itself or this particular mode. So, any questions? No? All right. Gonna hand you back to Sean. So his question is, how many channels can you have with, oops, how many channels can you? His question is how many channels can you have with like 2S and that was 2, basically 2. If you only want one, you get a channel with the data.
All right. Thanks, Justin. Okay, we're gonna briefly cover the other universal serial communication CIPs we have, right? UART, SPI, and I2C. Well, we have a extended UART module available. It could be synchronous or asynchronous. In synchronous mode, it can be either half duplex master or half duplex slave. In asynchronous mode, it can be full duplex. Well, we also provide auto-baud detection and wake up on break features with this UART. For SPI and I2C, we actually call it a MSP module. Well, for SPI, we support all 4 modes of the SPI operation. We provide SDO, SDI clock, and optionally a SS pin. For I2C, we have master mode, multi-master mode, and slave mode or supported. So you might be thinking, okay, what's new about it, right? Actually, with the aid of other CIPs, we might come up with some smart applications that can do things differently. So one of the example, how many of you guys have seen the example this morning? Oh, okay, awesome, this is the first time, yeah. So I'm gonna crush their classes. So one example that you might be interested in is we can actually use some of the CIPs to drive a serial lit string. Well, this might not be that trivial if you do some specific part, right? So one of the popular part in the hobbies or makers community is something called WS2812. Oh, this is a peculiar LED part. It has its own communication protocol. Well, the protocol from the database is, well, I encode my zeros and ones based on the path width. And the path width, they give you a table, tells you, okay, what is the maximum and minimum time it has to be. And it turns out, if I want to transmit a code 0, my duty cycle should be somewhere between 70% to 43%. And if I want to transmit code 1, it's going to be somewhere between 42 to 65. So there's a little bit overlap in the middle, but basically it's on both ends, right? Well, you could do it in a software way, do bit banging and other stuff. Well, it requires a little bit, it has a little bit requirements on the timing, or depending on how accurate your or how the real-time aspect of your MCU can go with, right? Some of the microprocessors might not be able to do it because they might be running on Linux or might be doing other stuff, and well, they just can't do the real-time in that that granularity, right? Well, software bitbanging is the most popular way of doing that. If you look at some online libraries that are all doing that in terms of talking to this LED specifically, but that's gonna cost you CPU cycles, right? So what we can do is, we've been thinking, if I have a SPI module, well, that naturally give you a 50% duty cycle if you do an AND gate between your data and your clock, right? Because your clock is 50% duty cycle, and if I have an AND gate with my data and my clock, I basically put my logic 1 out with a 50% duty cycle, which is well within this range. Now the only question is, how about my 0? For 0, I need something between 70% to 43, and obviously I don't want to go up to 43 because that's going to be misinterpreted by the device. So anything below 40%, just to be safe, that might be good. Well, that naturally leads us to a PWM module. which I can choose the duty cycle as whatever as I want, right? Then the following question is, okay, how do I combine them together? Well, there comes our favorite CLC. So if I have my SPI module, I can generate a 50% duty cycle for my logic 1s, and I have another PWM that I can generate somewhere, let's say 20% duty cycle for my logic 0s. What I have to do is just order them together. In the end, it will become my final output for driving this LED on the data line. Make sense? All right, so for example, I have some waves showing up here. I have logic 1s, which I want to put on the data line. All I have to do is AND my data with my clock. Then I get a 50% duty cycle. If I have logic 0s, what I do is I will add the negate of my data, which actually gives me zeros, with my PWM, let's say 20% duty cycle. Then I get my logic 0s. And finally, I OR them together. Oh, that's my 0s. If I OR them together, I get my final output as per the LED data protocol specification. Make sense? And put them into the hardware. I apply my SPI CIP, I apply my PWM. Of course, I need my CLC because I'm doing all those AND and OR get operation. I can easily just choose 3 of them from my CLC and do all the logic combination here, get my output. That way, you don't really need the CPU to do any software except loading the data to the SPI module and send them out. And all the data will coming out as per the LED data protocol specification, and you can drive the LED with your SPI. And some help from your PWM and CLC. Make sense? This is actually, I think, the lab for CIP1. If you are interested, you can check out this afternoon or tomorrow. All right, so those are basically stuff we wanted to convey today. To summarize, we introduced some of the various CIPs and their features, especially with examples, how are we going to apply them to serve our data communication protocol applications. And we also just briefly touched upon how can we apply the principle of combining different CIPs in a creativity way that I can combine them to serve my other data communication tasks, either to come up with your own customized data protocol or trying to make your application talking to the specified data protocol on the line. And just for the final word, if you are interested, you can always check out our dev boards. For the 16-bit, we have Explore 16 board. For the 8-bit, we have the Curiosity, which is a lightweight dev board. It basically covers all the CIPs that we have talked about today. And that's pretty much it for today. Any questions? Awesome. Thank you.